Hello ladies and gentlemen, this is Leftes from Greece for the Tricky Negro channel. In our exoskeleton project we used a lithium polymer battery pack to power up everything from high power electronics to sensitive measuring devices. We used a single pack because we wanted to keep everything relatively simple. So why the LiPo chemistry? Simply because they're highly available with low prices and they offer an extremely high power density. But when using them, apart from their operating temperature, one should be concerned about two things. Not to over-discharge them, either individual cell or the whole battery pack, and not to use or to draw extensive amounts of currents from them, more than they are specified to give by the manufacturer. Specifically in this video we're going to talk about the first problem and how not to over-discharge them. We created a module that converts the voltages from a balancing port of the LiPo battery pack that we have to voltages that an analog to digital converter in a microcontroller can read. Although there are a lot of ways of implementing that, from the humble resistor divider to active electronics using operational amplifiers and such, we developed a way with differential amplifiers that we believe it's the best, because it avoids grounding problems that can occur especially when using a high number of modules. I prepared a small explanation of our thought process and why we made the decision that we made developing this module, and hopefully you will learn something by it. Please stay with me, we're now going to the paper. So here we are in the paper and we can begin to explain a little bit our thought process. We can begin by enlisting our prerequisites, what we require for the module to do. One of it is to be able to measure each cell of the battery individually. And that is so that we can know the voltage of each cell. Why, you ask? Because a cell might be at a lower voltage than all the rest. Something that we cannot really see when we are measuring the whole battery altogether. And that can mean that this cell has a higher impedance, and when we are drawing a lot of current, this cell might overheat in relation to all the others, something that could potentially create a fire hazard, and this is a situation that we really don't want. Another pre-requirement is that we want to be able to leave the module connected to the battery indefinitely. That means that when connected to the battery, the module has to drain as little current as possible. So we can now start seeing a little bit of the available methods and explaining why we like them or we don't like them. The easiest method, but most of the times, or we should say a lot of times, especially when there are a lot of modules involved, is the simple and humble voltage divider. So we have here in a relatively simple example. A voltage divider is nothing else from two resistors. These resistors are, as we will explain later, have to have specific values so that they can be connected to the ADC without having a problem. The ADC will only support a certain characteristic impedance. It will not support every voltage source. You cannot read any voltage source, and for an average ADC in a microcontroller, that maximum impedance of a voltage source is usually around 10K. This is something that we can correct a little bit with a capacitor like this here. But that's also creating other problems, like you should ensemble this circuit as fast, you should wait for this capacitor to be completely charged and then assemble this channel again. It creates a lot of mess and it's not something that we like. Plus it has the problem that all the grounds here should be connected together, and this creates alone a big problem, as we will see later. Sure enough, it's an easy and dead cheap way to implement a voltage reading from the battery cells, and when you want, you can also expand this to all the cells, not only the whole battery as it is. And you can also have some alternatives, as you can see here. You can, if for example you would like to use high values resistors here at the input so that you don't drain your battery, you can use an active circuit with an op-amp, with a voltage follower. Of course, there is also a lot of ways of implementing that. You can have a simple voltage you can simply make your resistor divider here and have a simple voltage follower where the negative input connects directly to the output. You can compensate a little bit for the input current of the op-amp with having resistors. These resistors in parallel here, matching the characteristic impedance of the voltage divider. And of course, you can either drive the ADC pin directly or either use a filter. That can also help a little bit, and that also depends a little bit on the operational amplifier that you are using, and it's something that you have to care about and have in mind. Some other problems that this configuration is creating, and we will explain in detail later why this is that it limits a little bit your options about soft switching, and we will analyze this later. And I will also propose a circuit for soft switching and see how useful it can be. And of course can create this grounding problem that we told about earlier. But why does it really create this grounding problem? Sorry, I forgot to say here that of course if you want to use this method or this of the active alternative, you have to calculate a different voltage divider here for each individual cell, because across the first cell you're going to have, you know, a voltage from 2.5 until lowest 2.5 until 4.2, and then the next cell is going to have this voltage plus the voltage of that cell, and so on. So you have to calculate its resistor divider again and again and again. Also, another thing is that the non-active way can create some errors and non-linearities. I mean, these errors and non-linearities you always have. There are ways that will not show here to correct them with such passive circuits here, and these non-linearities are mostly coming from the ADC. These non-linearities and errors can be a little bit corrected by the active alternative, but you need to have a specific circuit so that you know how big your error is, and you can use a specific channel of the ADC to just read your ground. It's what it is called, but this is not the theme of this tutorial, so I'm not going to say anything further. What I'm going to do is bring you here, and I have to zoom out the camera a little bit to explain to you exactly what I mean with the grounding problem, which is the main problem that we wanted to avoid in our project. You have a LiPo battery, like this one here, right? You have your power leads that you connect to your ESC, your power electronics, your whatever you want to connect them to, and you have the balancing port, something like this here. The balancing, if you see inside the balancing port is like this. It's direct connections from each individual cell to this JST or whatever connector that you have. But these are direct connections. This means that this pin, the lowest pin of the balancing port and the highest pin of the balancing port are going to be directly connected also to your main power leads. So by having this system here, we can see that, you know, you have your main controller here that has all your accelerometers, your gyroscopes, your logic, your microcontroller, whatever you want to have inside this. And then you have your main ESC. Now, most ESCs that are available to hobbyists and are available from various companies are not isolated. That means that the inputs here are not isolated from the drivers and the MOSFETs. So the ground of the ESC is going to be also the ground of the input and also the ground of your main controller. And of course you have here your main power leads that connect directly to the ESC. One is power, the other is ground. And then you have your load that you're driving, either your brushed or brushless motor or whatever you want it to be. And you want to check the voltage of your battery so that you connect the balancer port to your main controller. But then again, coming back to this paper, you see here the grounds are common. The grounds are common here, the grounds are common here, the grounds are common in your ESC. So a very big problem is created. Are you sure that your current is only flowing from your main power leads to your ESC to your load, or is some current going from the balancing port through your main controller to the ESC? And that's a really big problem, especially when you are running electronics, measuring electronics around like ADCs and stuff. It can create a whole mess. And another really serious problem is that, say that you change your battery or that you do the mistake and plug the balancing port the other way around. You have effectively sorted out your battery through your balancing port, because this pin down here is going to be up and the up is going to be to the ground. So through your main controller you have actually sorted out your battery, and it's a LiPo battery. You can draw a heck of a current out of these batteries. For example, I don't know, this battery, I think you can draw something like, it says here 200 amperes. 200 amperes through the small traces of your main controller. That is going to be a catastrophic failure. Either your balancing port cables are going to melt, or either your controller's traces are going to melt, and this is something that you don't want. Apart from the case that you want to win a Darwinian award, but I think that you are here so that you avoid this. So another thing is that then with soft switching, and what do I mean with soft switching? And also with current sensing. A lot of times you want to control the current that goes to your power electronics. A lot of times you want to always provide power to your main controller here, be able to monitor your voltage, and let's say that if the voltage drop of an individual cell here, or the whole battery pack drops below a point, below the threshold that you want it to drop, you want to cut power to your power electronics, but not your main controller. And how do you do this? Of course, what you can do is use a MOSFET. Now, a lot of people will say now, why should you cut the ground effectively, and why wouldn't you cut the positive rail? The thing is that, as I have explained here, that with high side soft switching, you have to have a P-channel MOSFET. Or if you still want to use an N-channel MOSFET, you have to have a higher than the battery rail so that you can switch the gate, because the gate of a MOSFET, of an N-channel MOSFET, has to be more positive than the source in order for it to conduct. So in the second case, you have to add to your circuit a boost circuit or switching circuit that you might not want to add, that it takes space, that might create noise and all the stuff, and it's really something that you want to avoid. If you don't have to produce an extra rail in your circuit, you don't want to produce that extra rail in your circuit. And with P-channel MOSFET, the thing is that the only resistance of most P-channel MOSFETs, generally, at least from what I've seen until now, is going to be higher than an N-channel MOSFET, or at least you can say that the relations of on resistance and price, it's much better for N-channel MOSFETs than P-channel MOSFETs. That's why you would want to use an N-channel MOSFET and low side soft switching. And that is the case here. But you know, if you cut the ground here, let's say that you cut the ground at this place for your power electronics, or the negative rail, you should say more specifically, then you have the problem that all the current is going now through your balancing port, and effectively you have done nothing. You haven't switched off your power electronics, and you're drawing a hell of a current through small traces that can also be relatively catastrophic. You don't want that. Another thing is when you want to sense current at the low side. So why to sense current at the low side? Because it's much easier. First of all, it's much easier to pick up an op-amp for this job, and it's really much easier. You don't need to use a specific current sense op-amp that might be more expensive than your regular op-amp, and also most of the current sensing op-amps have fixed gains. That's another thing to consider, and it creates a lot of problems. And of course, what's going to do in a current sensing circuit like this, let's say that you have your current sensor here, you have your main current coming from the battery, ignore this control soft switch, and you have here your current sensor, and you have your shunt resistance. But that shunt resistance is going to be somewhere here. Again, how do you know that the current is not coming from the balancing port and ignoring completely this current shunt? Or you can say that you have two current shunts, one that you monitor with your op-amp here, and one that is created through the balancing port and your main controller, and all these small wires that you have to connect in between. So you really have a problem. So you either switch to high side current sense and soft switching when you want these abilities, when you want your project to have these abilities, let's say, or you have to do something about this balancing port, about the ground of this balancing port. You cannot simply connect the ground of the balancing port to the ground of your main controller. That's a scenario that it's not really possible. And to explain to you how nice it is, really nice to have soft switching in your circuit, I'm going to show you a small example of it and how practical it can be. So let's say that here you have your main power MOSFET that all the current goes through. It can be any power MOSFET. This is something that you have to pick up, and I will explain a little bit later how you should pick this MOSFET up. So here you have your positive rail from your battery, and you have a couple of let's say you have like a small filter. So what you do is you have a toggle pin from the microcontroller. This toggle pin is you can toggle this pin either from a timer, or you can toggle it from software. So you know that this pin is always going to toggle as far as your main code is going to run. That is also the reason that you have a capacitor here, so that if your program gets stuck, or if the oscillator of the microcontroller gets stuck in one state, then it will not let me focus a little bit the camera here so you can see it better. I think that's good enough. Okay, so that's why you have the capacitor here, so that you know if this pin stays in a specific state, it will not keep this transistor up. So effectively, what are you doing? You are just switching on and off this transistor. This is a NIP transistor. You can use an N23904 that is good for switching and all the stuff. That's what transistor you use, you just need to use an EPN that then the collector voltage can go as high as your voltage rail here from your battery. And then again, this transistor is switching a PNP transistor. And what this PNP transistor does really, what it does is that it charges up this capacitor. This capacitor is directly connected, or at least through a small series resistor, to the gate of your MOSFET. So by switching this transistor, you effectively switching this transistor, which enables current to flow into the capacitor, or whatever you want to call it, and thus charging the capacitor up to the voltage, at least of the battery. This is something that you have to be aware of. It's not going to charge it higher, probably it's going to charge it a little bit lower than the battery. So this capacitor, as far as this pin is toggling, is going to have a voltage, and this voltage, you can go ahead and calculate it, will be high enough to turn on this power transistor. So as soon as your microcontroller is toggling this pin, you know that your power electronics have always power. And what you can do here is that you have a soft switch. This is like a small switch. It doesn't have to be a big clanking switch that bypasses this transistor. So let's say that you have a switch here, you press the switch and you charge up this capacitor to the voltage of your battery. So you turn on this power MOSFET, your microcontroller gets voltage, and as soon as it does its basic checkups, if you want to check up anything, then it starts toggling this pin. So then it self-sustains the power to the circuit. If something happens, if your battery is low, or I don't know, you had an overcurrent condition or whatever, you can stop toggling, or the main program halts for whatever reason, or the main oscillator halts, of the microcontroller halts for whatever reason. This toggle pin stops, and through this bleeder resistor, the voltage of the capacitor here is going to empty. And because of that, the power MOSFET is going to close. No power to your power electronics. No way that there is going to be a major accident if your microcontroller is starting to send rubbish to your power electronics. Also, what you should note for choosing up this power MOSFET and this zener here is to limit the voltage across the capacitor, and you should have it when you have, I don't know, generally you should have it, and it really depends on the MOSFET. There are MOSFET that they are like logic level power MOSFETs that they will switch on from a gate voltage up to 3 volts, and that's fine and dandy. And so you have to be really careful when you are choosing this MOSFET, because you have a certain battery voltage here. For our case, it's a big 4-cell battery. It's going to be 14 volts, and our power MOSFETs can handle up to 10 volts per gate. So our zener here has to be like 9 volts. I don't know how to explain it a little bit better. So you want that the MOSFET turns on completely and it's out of its linear region at a gate voltage that is lower than the input voltage here, so that you can be sure that when you have voltage across this capacitor that your power MOSFET is switched on. But this voltage shouldn't be as high as to kill the gate of the MOSFET, and thus you're having this zener. But this is something that you have to go ahead and calculate depending on your MOSFET that you choose. So you have a very practical example of a battery, of a soft switch, because not only you can, with a relatively low current switch, especially when you're handling here 100 amps and 200 amps, whatever, with a low current switch, a tactile switch basically, you can turn on your whole circuit, but you can have a failsafe here that when your microcontroller is doing something bad and something wrong, or your main code is not working, that this will stop to work. The power is not going to get to your power electronics, and that's really something that you have to be aware about, that when your microcontroller has a problem, then it will not blow up the rest of the circuit. That's why soft switching is so important. And because, of course, N-channel MOSFETs are much more cost effective, at least nowadays, that's why you do low side soft switching. But this will not be able if you're connecting directly the ground of your balancing port to your main CPU. So we'll go ahead and discuss a little bit what we can do. So we can see a little bit of basics before we go ahead and understand our final circuit. A very important theorem that you should know for electronics is Thevenin's theorem. It pretty much says that, for example, if you have a resistor network or a resistive divider like this one with the voltage input and the voltage output, that pretty much equals as a voltage source, that the voltage of this source equals to V out here, and the characteristic impedance of this voltage source equals the parallel combination of R1 and R2 as displayed here. It is very important and can be generalized also for imaginary resistors or impedances and all the stuff. You can let your imagination do whatever the things you want to do, and really it's a very powerful theorem and something that you should really know about electronics. We can go ahead a little bit and generalize the humble resistor divider. Let's say that we want to have here an voltage offset for whatever reason that we want to have it, and we want to get the V out here. So it pretty much ends up to this equation. What's only going to change from the simple resistor divider is that you have to add in the voltage offset at the voltage source here. The impedance of this voltage source is again going to be the parallel combination of R1 here and R2 here. So it can be pretty much generalized as this, and it will help us to do some math later on in the circuit. So we can go ahead and see the main building block of our circuit, and of course the main building block of our circuit is the differential op-amp. What is a differential op-amp? As its name suggests, the differential op-amp amplifies by a certain gain, which gain is set by R2 over R1. R2 is here, R1 is here, and this should be mirror exactly the same for sakes of symmetry and common mode input rejection and CMRR for common mode rejection ratio and all the stuff. This can be a video on its own. I'm not going to overgeneralize about this, but you should have as a general rule that this resistor and this resistor should be the same, and this resistor and this resistor should be the same. So you have voltage input here, and pretty much what it does is it amplifies this voltage and its output by a specific gain set by these two resistors. And what I haven't seen in a lot of explanations I found on the internet is that here most of the people you see connect ground to this resistor. This doesn't really have to be ground. This can be any voltage, and this voltage is going to be your offset, your output offset. It's going to be just added to the result of the differential op-amp, as suggested by this equation here. Because the voltage output of all this device is just the difference in this the voltage difference in the input, which can also be referenced to the ground as it is in this circuit, like VB here as the positive input minus VA as the negative or inverting input, multiplied by the gain set by the resistors plus the voltage offset that you have here, and this is pretty much the output of your differential op-amp. And it's a pretty useful circuit. The differential op-amps can really do miracles in a lot of stuff. Their noise rejection is excellent. Their common mode noise rejection is excellent, and for it to be really good, as we stated before, these resistors have to be this R1 and R1 tone should be exactly the same, plus R2 and R2 tone should be also exactly the same. Also, you want, when you offset the voltage output of your differential op-amp, you want that the characteristic impedance of the power source of your offset is relatively low, and I mean a couple decades lower than R2, so that you don't have to calculate here the extra resistance. So without further ado, we can go ahead and see a little bit our final circuit, and I hope I can explain it as best as I can. So pretty much you begin with having your battery here. This is the first cell, then you have the next cell, and the next cell, and the next cell. So what you want really is not to get the voltage of its cell, but what you want is actually to get the voltage of its cell, but not the voltage reference to the ground of the battery. That's why you use a differential op-amp, or a circuit that looks like a differential op-amp, which we will see it's really a differential op-amp with extended common mode input range. And you don't want to amplify here a voltage that it's referenced to the battery ground. You just want to get the voltage across its individual cell and multiply it by a specific gain, and then send it to your ADC. So it turns out, if you do a little bit of the calculations with all the math, you probably have everything that you should have with what I've shown you before. So you end up with this final output equation, which is pretty much the same as a classical differential op-amp. So why the need of these resistors? Because, you know, the voltage output is R3, like here R2, over R1, like here R1, multiplied by the input voltages plus the output offset here, and not the input voltage here. The input voltage actually gets out of the equation if you do all the math. So why do you really add all this? Why do you add this voltage offset at the input, and why do you add these resistors? And the answer is really common mode input range. The voltage the input voltage at the pins of the op-amp cannot go higher or lower than the power rails of the op-amp. So let's say you power the op-amp from 5 volts regulated, then it cannot reach as high as 20 volts or 14 volts that you have up here in the battery, because here the difference in the final cell is going to be like, I don't know, it's going to be 10 volts and 14 volts here. So 10 volts and 14 volts here are much higher than the 5 volts that you're powering your op-amp from. So you need to extend the input range of the op-amp, and to do that you pretty much put these resistors. So in the end what you have is that this acts as a voltage divider, but then again, if you see here the math, these resistors get out of the equation for the gain and only the gain, not the common input range. That means that when you have these two networks here, the inputs here are not going to be as high as, for example, for the first cell, 4 volts. The input here is going to be, I don't know, 1 volt if you want, or whatever your values you want them to be. This will be better explained in the example we will do after. But you don't want the inputs of your op-amp going above or lower the rails. You're going to activate the ESD diodes inside the inputs and you're going to have serious problems. That's why you put the this voltage divider, these two voltage dividers, instead of a single resistor like this one. Even if these resistors are high enough, you can never really predict what the voltage is going to be here. I mean, you can predict, but in the end it's much safer to use something like that. And we have here a voltage offset, and you might be wondering, why do we really need this voltage offset? Because the thing is, as we've seen here, the generalization of the humble resistor divider, you pretty much don't want to be very close to 0. You don't want to drive this pin very close to 0 or below 0. Because, as we mentioned before, and I'm going to switch a little bit the papers here and bring you a little bit back, if I actually find what I want to find. Yes. So, as we mentioned before, we have pretty much, you know, our current sound and our soft switch and all the stuff. So, across this resistor and the on resistance of the MOSFET, there is going to be a voltage drop. That means that most probably, and also really depending on the current that goes through here, the battery terminal is going to be more negative than the ground or the ground reference of your main controller board. So you want this voltage offset here to pull up a little bit the value here. So if you go, let's say here, this is the ground of the battery, but the ground of the battery might get, I don't know, let's say -1 to the ground of your main circuit. You want to have a voltage here that actually pulls that voltage up. You don't want to reference here this. You don't want to reference these two inputs to as low as to the ground, because then here this point is going probably to get more negative compared to the rails of your op-amp. That's why you really want to use this voltage offset, and this will become a little bit more clear when I go to the example. And this is what I should do now, if I'm able to find my papers that I throw around somewhere here. So here we have the example. Should be all fine and dandy, and pretty much this is an exercise. Let's say, like our case here, that we have a 4-cell LiPo battery and we need to measure each cell individually and also keep ground separate for all the reasons described above. Oops, sorry, that should be a little bit lower here. Yes, so here you have the main line. And also we know that, you know, we want to use rail-to-rail input-output op-amps. Most of these op-amps are CMOS op-amps, and their range is not really, their voltage range is not really high. For example, the ones that we used cannot work with more than 5 volts. Not the inputs, but from where you power them up, your power supply shouldn't be higher than 5 volts. And we are going to make so we can go ahead and calculate now that we can make the basic assumption that the voltage across each cell is going to be between 0 and 5, we want to give a little bit of room for error and non-linearities and input current offsets and the offset of the op-amp and all the stuff. We want to give a little bit of room here, a little bit extra room for play. That's why we say it's between 0 and 5 and not 4.2. We lose a little bit of resolution in the end, but we're a little bit on the safe side as for overvoltaging and stuff like that. So the difference across the cell is going to be 0 and 5 volts. Very well, and it's also a very convenient number. Why not to use it? So we'll go ahead and say we want to find out the characteristics of our input device, and our input device, of course, is an analog to digital converter. We can say that the analog digital converter can get a voltage between 0 and 5 volts. So the maximum V out of our differential op-amp, and I don't know, can I have both of them too here and zoom out a little bit? No, the other way around, please. Not really. Okay, I keep it zoomed in and we can see it here, and I can change the papers in between. So let's say that the maximum, so if our ADC input is between 0 and 5, we want also the output of our op-amp to be between 0 and 5, and we know that the maximum difference across the cells here is also 5 volts, so we can go ahead and calculate voltage offset. In this occasion, we don't need at the output. It can offset from 0, or the ground, you can say. So we pretty much have this. The V out is 5 volts at the maximum. You want to calculate for the maximum first, and V in is also the maximum, it's 5 volts, so we pretty much get the ratio of R3 and R1 as R3 and R1 here. So then after we have the ratio here, knowing our inputs and outputs, we can go ahead and say what value resistors we want. And this is something that you can pick up by yourself. You maybe not want to pick up a very high value resistance because it really depends on your op-amp and its input input leakage, input currents and offsets and all stuff. You should go ahead and calculate it yourself, but it will really depend. The value of these resistors will depend on your op-amp. For us, we found out that 470k was a good enough value that wouldn't require a lot of current from our battery. I haven't really calculated how much current you draw with this resistor from your battery, but it should be around a couple nanoamps. You can pretty much get lower using 1 meg here and stuff like that, but that really depends on you. That you can go ahead and play around. It depends on what you want to do and your op-amp and you select and your final application, all the stuff. So about the common mode input voltage that I would most like to explain here is that we know that the maximum voltage is going to be around 20 volts because we have 4 cells. Each cell has a maximum of 5 volts. 4 multiplied by 5 equals 20, and we can say, you know, our vein, the maximum is going to be around 20 volts. The minimum is going to be around 0. So we have a dynamic range of 20 volts, you can say. So we want to go ahead and calculate this ratio, and this ratio, these resistors R2 and R1 and R2, it's pretty much these resistors here, and this should equal or be less than 5 volts, which is, you know, at the same time the power rail of this op-amp. That's because this is pretty much going to be your input voltage here, and you want to be less than 5 volts so that your op-amp doesn't have a problem following your inputs. We went ahead and said, you know, we should leave a little bit of space, our op-amp is good enough. So we chose a resistor value of 30k, it's round enough. It's not really easy to find, but we used 3 times 10k resistors, so that was pretty good. And then we get, you know, a dynamic range, a common mode input range, let's say of 80 volts. And now we pretty much know that, you know, each input here can go from 0 to 80 volts, no problem, as soon as the difference here is kept at 5 volts or less. If it's more than 5 volts, it's not going to blow up something, but it will max out the output of your op-amp, so you will get simply garbage. But the thing is, as we said before, because of the circuits that you might have, the short switch is the resistance of the power leads themselves. This, the ground of the battery, the negative of the battery, let's say, it's going to be a little bit lower than the ground of your main controller. So that's why you put this voltage offset here. You really want to get this common mode input range, you want to offset it a little bit more negative. And to offset it more negative, you get here a positive voltage. And I've done here a very simple table that when you say this, let's put it like this, you know, when this voltage offset at the input is 0 volts, the common mode input range is between 0 and 80 volts. That means that these two inputs can go from 0 to 80, and this input can go to from 0 to 80 independently. And when you offset it by 1.25 volts, as we did in our project, we ended up with a common mode input range of roughly minus 20 to 60 volts. That means that this pin can go as low as 20 volts, and this pin also high as 60 volts, without the op-amp really producing garbage at its output. Then again, you can go and say you want 2.5 volts in the input offset, and then you're going to have a common mode input range from minus 40 to 40. Then you can go even to 5 volts here, and then you can say to minus 80 to 0, and so on and so forth. It never ends. But really, you can start a little bit experimenting with all the stuff. I think this is a really neat circuit. It's really basic, and it really provides a very good way of measuring the voltage of your battery. And generally, you doesn't have to be the battery here. It can be whatever voltage source you want. It can be a microphone. It can be whatever you want. Because also microphones, some elect microphones, you have to bias them with the resistor and stuff like that. It can be whatever. It doesn't have to be a battery. That circuit, you can use it for whatever you want. Of course, the same for the classical differential op-amp. This, let's say, an extended version. A version of a classical differential op-amp where you can increase the common mode input range. So, without further ado, and as a final part of this video, I'm going to show you the final module, what we've done. In our example, R3 is 309 kilo ohms, for the reason that we want to interface the whole thing to a 3.3 ADC, 3.3 volts ADC, and let's go see how it works and finish this video. So this is the final module that we prepared for the project. We use two dual operational amplifiers The model is OPA 2333 from Texas Instruments. They're quite nice. They're CMOS, they are rail-to-rail input and output. They have pretty sleek power consumption, really small quietness current, and all the stuff. They're pretty good. Go ahead and check them. And also we used for the voltage input offset, we used each voltage reference individually for each channel. In the end it was not really needed. We could have used only one voltage reference for all the voltage input offsets. We were just worried at the time about channel crosstalk. That's why we didn't do that. So pretty much you have the inputs of the battery here going into our, I don't know if you can see it. There's pretty small, and I don't know if this thing is willing to focus. Maybe if I throw it completely out, it can do something, but then I don't have light. Yeah. So I'll try to keep it a little bit here and explain. So here are our input resistors. This 470 kilo. Then we have 3 resistors of 10k. We didn't want to order extra 30k resistors. The resistors, by the way, are from a company called Susumu. We got them from Mauser for around 2 euros for 100 resistors, which for mass production it might sound expensive, but for our relatively small project needs they were totally perfect, because they really had a very good temperature coefficient, and I think they were 0.5% accurate, absolute accuracy and all the stuff. So they're pretty good for our purposes here, especially for measuring a battery. So we can go ahead and test the module. Again, as I said before, this is a module designed for a 3.3 volt microcontroller. So we hypothesized that the inputs are going to swing, the differential inputs are going to swing between 0 and 5 volts, and the output is going to swing between 0 and 3.3 volts. So with the battery voltage we get around 2.5 volts. The battery voltage is around 3.8 volts right now per cell, and the output's like 2.5 volts something. We can check with the DMM later. So the first thing that we want to see is how it behaves when we connect the battery. Right now the module is not powered, and I'll go ahead and connect the battery. The black lid here is the negative terminal of the battery. So normally it connects like this. We see nothing happens, no magic smoke, no electrons fall from somewhere or anything. But let's say we make the accident and we connect the other way around, that we shouldn't, and still no magic smoke, everything fine and dandy, everything cold and nice, cold and cool. And what we can do now is, I don't know, go ahead and give power to the module and use a DMM to measure the stuff. I know for sure that each cell of the battery here is around 3.8 volts. Because I'm doing everything from the screen of my camera, I don't want to try to probe around the battery inputs in case I do something wrong and I win the Darwin's award, and I don't want to burn down the only house I have. That would be really bad. So let's go ahead and connect the battery how it is supposed to be connected, with the power on. I'm powering, by the way, the module from an external source, not the battery itself, and it's like how we wanted. It shouldn't matter at all, and it doesn't matter because we still get a reading at the DMM. So I don't know how I will be able to squeeze everything inside the screen. So I'll try to go ahead and you can see the DMM clearly. That's a good thing. And I should have it here. And I should be able to probe somehow. Fucking thing. So I'm probing the ground. And now this is the first output. Can you see? It says 2.5. Sorry for the image, but right now I'm alone and I cannot do something better. From the second cell, the output it's 2.5 something, again 2.5 something, and again 2.5 something, and of course everything is applied from 5 volts. Where is it? 5 volts. So everything works, everything is perfect, everything is cool. And this is exactly what we wanted from the beginning. A module that the ground of this module doesn't have to be the same as the ground of the battery, that can measure the battery with pretty much high input resistance, and that's all. I mean, the operation of the module is not really exciting, it just works as supposed, but it's just for you to see that it really works. You can go ahead and connect it to a microcontroller, do whatever wonderful stuff you want to do. As I told you, now you have all the equations you pretty much need to make your own project. You can use the same schematics also to plan current shunt monitor. You can do whatever you want. So that's it for me. Thank you for watching. Like the video if you like it, dislike it if you dislike it, leave a comment. Your feedback is very important, especially when it's a negative one, and hope to see you next time. This is Leftace from Greece for the Tricky Necro channel. Bye bye.